Yeah, I think we should start.
Okay.
And I'm glad to announce our last talk of this first Eastern Hemisphere session. And our speaker is Philipp Schmitt from University of Copenhagen, who will talk about quantization of coadjoint orbits.
Okay, thank you for the introduction. Thank you for giving me the opportunity to speak here. And also thank you for organizing this wonderful workshop with all the social activity and so on and so forth, which is probably quite new for a lot of people. At least it will be new for me. Okay, I hope everyone can hear me well, and I hope everyone can see my slides. Good, perfect. And with that, let me just say that this is mainly the results of my PhD thesis, which I handed in 2 weeks ago at the University of Copenhagen. And it's mainly about quantization of coadjoint orbits. So let's just get started and basically with a very short recap of the quantization problem. So the idea is we have a classical physical system. So that is usually described by, thanks Nikita. That is usually described by a Poisson manifold M, and the observables, so the quantities that we can measure, are real valued smooth functions on this Poisson manifold. And now the time evolution is usually just given by the fact that the time derivative of such an observable is given by the Poisson bracket with a so-called Hamiltonian function. And this Hamiltonian function essentially describes the energy of the system. Okay, on the other hand, we have quantum mechanics. And in quantum mechanics, we usually consider some Hilbert space H, and observables are then some self-adjoint elements in some algebra of typically unbounded operators on this Hilbert space. And even though this algebra a priori looks quite different, the time evolution is very much similar to the classical case. So again, the time derivative of an observable is given now by taking the commutator with a so-called Hamiltonian observable, again describing sort of the energy of the system. So from a mathematical point of view, if you look at the mathematical structure, then on the classical side, we have the smooth functions on our manifold together with a Lie bracket, and this Lie bracket is just given by the Poisson bracket. Whereas on the quantum mechanical side, well, we have a non-commutative algebra, and then the commutator rescaled by this I times H bar that serves as a Lie bracket. So sort of the observable algebras, their structure is rather similar, and well, you all know that classical physics is sort of a very good approximation on macroscopic scales, so in everyday life. So if you let H bar, this parameter which sort of describes how quantum our system is, if that becomes small, then we would like to recover classical physics. And on the other hand, the quantization problem is essentially the problem of associating to a classical system some quantum system in such a way that, well, essentially we recover the classical system again when we let H bar tend to 0. Okay, and well, when I say here quantum mechanics, I usually want to basically forget about the representation on a Hilbert space in the following, and I want to focus on the observable algebra up here. And essentially I would like to have, or I would like to think of it as some, well, for every value of H bar, we basically have some algebra. So we really have a field of algebras. And then how does classical physics arise from that? Essentially, it arises if you just look at the limit where H bar tends to 0, and then only remember the first order approximation. So this Poisson bracket sort of plays the role of a first order infinitesimal. And well, now we can also look at the infinite order infinitesimal, and that will just be a formal deformation quantization, as you have already seen it in the last talk. And I will again define it on my next slide. So in a sense, that is just you take your whole field of algebras and you look at the Taylor series expansion or the jet at H bar being 0. Okay, and in a sense, you can view these formal deformation quantizations as splitting the quantization problem into 2 parts, namely one algebraic part and then one analytic part. That if where first you try to sort of upgrade your first order infinitesimals to infinite order, and then you somehow try to make sense of these power series by somehow seeing whether they're convergent or not. So that usually is an analytic problem. And well, what I want to do in the basically rest of the talk, I want to explain to you how, for the special case of coadjoint orbits, how to actually construct such fields of quantum algebras in a Frechet algebraic world, which, well, I will say something about in a minute. Okay, but for now, here's the brief reminder about the formal deformation quantization, as we have already seen it in the last talk, and as it was introduced by Bein, Flato, Fronsdal, Lichner-Horowitz, and Sternheimer. And I will essentially use the formal star product and the formal deformation quantization interchangeably. So if we start with a Poisson manifold, such a formal star product is just given by a product on formal power series of smooth functions. It is assumed to be associative, which is very important, and well, bilinear over formal power series, such that, well, when you expand it, so when you take two smooth functions f and g, the result of that multiplication is in general a power series. So if you expand it as a power series, these operators CR, they should be bidifferential operators, so that you can actually restrict your star product to open subsets because it becomes a local operation. And well, we want to have the correct limits, as already in the last talk. The 0th order should be the product, and sort of the commutator in 1st order should reproduce the Poisson bracket. Okay, and then there's one more technical condition, namely that the constant function is still a unit for this deformed product. And I should say here that I will always use nu as a formal parameter, and I will always use h bar only for actual complex numbers. Okay, so whenever you see an h bar, you already know that that is really a complex number, and whenever you see a nu, that is going to be a formal parameter. Okay, and well, then there's a famous theorem by Kontsevich, or it's a consequence of his formality theorem, that these formal star products actually exist on any Poisson manifold. Or in different words, whenever you have one of these 1st order infinitesimals, like a Poisson structure, you can actually quantize it to such an infinite order of formal deformation. Okay, and well, Kontsevich not only gives an existence result, he also sort of has a way, or it also, from his theorem, it also follows that you can classify these formal star products up to some notion of equivalence. But that will not be relevant in the following. Okay, so let me maybe continue by telling you that it is not completely trivial to actually come up with such a field of algebras that has a correct expansion. And let me illustrate that by one example, which actually works in a equivariant setting. So if we just have an action of a Lie group on all the objects that we're working with here, and then ask all the products to be equivariant with respect to this action, then we can actually, then there is a theorem by Riefel, which essentially tells us that already for the 2-sphere, we cannot sort of quantize it in a nice C-star algebraic way if you also require equivariance. So here is the statement of the theorem. Basically, if we take the smooth functions on the 2-sphere, and well, whenever we now consider a new product that is non-commutative on the space, such that for this product there is some involution, some star involution, and some norm, such that the completion with respect to that norm becomes a C-star algebra. Okay, and if you also assume that the rotations, just as the special orthogonal group, just acts on the 2-sphere as usual by rotations, and then on the smooth functions by pullback, and that this action is isometric and a star automorphism, so nicely compatible with this product and this involution, then it turns out that this product is automatically commutative. And well, in a sense, what this means is whenever we try to construct, say, C-star algebras over here that sort of contain the smooth functions on the 2-sphere, and whenever we try to do that equivariantly with respect to this action of SO3, then these algebras here will automatically be commutative. So sort of whenever we try to look at the Taylor expansion, well, all Poisson brackets that we can quantize in this way will automatically be trivial. Or in other words, well, an equivariant quantization of the 2-sphere in a C-star algebraic setting, and such that all these C-star algebras sort of contain the smooth functions, that is simply not possible. Okay, and well, let me say that it's already enough to assume that it contains all the polynomials on the 2-sphere. So we can, yeah. So in a sense, that tells us that this problem of passing, say, from a formal deformation quantization to some actual field of algebras, that is at least non-trivial. Of course, one can argue that one should also sort of quantize the action of SO3 and so on and so forth, but I just want to use this to illustrate that this problem is actually, or can be non-trivial. And well, what I want to do in the following is I essentially want to propose a way to sort of not use C-star algebras, but to use so-called Frechet algebras, and to obtain a field of Frechet algebras that sort of quantize coadjoint orbits just as presented on the first slide. Okay, and here is an essential approach that was proposed by Beiser and Waldmann and carried out in many examples by some collaborators of them. And the idea is essentially we take all the information of a formal deformation quantization into account, and it is sort of, as we've seen on the last slide, easy or relatively easy to find such formal deformation quantizations, or at least their existence is well understood. So we start with such a formal deformation quantization, and then we simply ask whether we can find some subalgebra of functions for which the formal power series are not infinite series, but just finite sums. So meaning, if we take two elements P and Q of such an algebra, we just want P star Q to be a finite sum. And well, if you have a finite sum, then we can just replace this formal parameter nu by an actual complex number, and we obtain a real family of products. So that means for every value of H bar, we just get a product on P on the subalgebra that we chose in the beginning. And of course, such an algebra might not exist in general, but at least in a lot of examples, for example, coadjoint orbits, it will exist, and there will be a canonical choice of such an algebra. Okay, and then finally, we can try to find some topology on this algebra with respect to which the product is continuous, so that first of all, the product extends to the completion. And while the idea is just now we have a topological algebra, which is nicer to work with, for example, when we want to study its representations. And on the other hand, this algebra contains more interesting functions that we can possibly quantize because we have completed the algebra that we had before. Okay, and now in the rest of the talk, I would essentially like to explain to you how this works for coadjoint orbits. But since this is a bit technical, I will restrict myself to one special case, which is essentially complex projective space. And remember that the two-sphere that we've seen here is just complex projective space with complex dimension 1. So that is included in an example. And this case is sort of the one that is relevant for many C-star algebraic quantization procedures, or say this example is very hard, or it's a very hard, many quantization procedures fail for the two-sphere. Just put it like that. And what I want to present to you now is essentially something that works for the two-sphere for complex projective spaces for arbitrary coadjoint orbits in a Frechet algebraic setting. Okay, so here's the idea. I will mainly try to explain to you now which algebra we can use for these polynomial functions and what the completion of that algebra is. And so the bottom left corner, that will be what plays the role of the polynomials. This A of CPN will be the completion, and this upper row is used to define these algebras, and I will explain to you this diagram in the next 1 or 2 slides. Okay, so what is the idea? First of all, very brief reminder, complex projective space, while you have an action of C without 0 on C1 plus n, just by component-wise multiplication. And then you essentially just take equivalence classes, and that gives you complex projective space. And now to define polynomials on complex projective space, we start with a polynomial on C1 plus n. We assume that this polynomial is invariant under the group U1, acting on C1 plus n just by component-wise multiplication. And then if you have such a polynomial, we can essentially restrict it to the sphere, sitting inside C1 plus n. And then we can remember that CPN is just a quotient of the sphere by the action of U1. And well, since our polynomial was assumed to be U1 invariant, it will descend to CPN. So, and all the functions we obtain in this way, so all the functions that can be written as, that can be obtained in this way, that is what we call the polynomials on CPN. Okay, here is how you should think at least about these U1 invariant polynomials on C1 plus n. That is essentially just to take coordinates, Z1, Z0 up to Zn, and then these polynomials will be polynomials in the set i's and set I bars, so they're complex conjugates, such that well, each monomial has exactly as many sets as it has set bars. Okay, so that should tell you what this lower left corner is. And now I need to explain to you what I mean by the CP hat N, which is sort of some larger space than complex projective space into which the complex projective space embeds. So here is the explicit definition. It is just a subset of CPN times itself. And it is the set of those pairs which essentially are not having scalar product 0 with each other. So we just take CPN times CPN, and then we essentially remove those points where all the that have scalar product 0. So in particular, the CPN hat will not be compact anymore. And in particular, there will be non-trivial holomorphic functions on there. And well, the regular CPN just embeds into this extended CPN if you just send an equivalence class of a point Z to the equivalence class of Z and its complex conjugate. And now it's easy to check, well, if you evaluate this condition, well, Z times Z bar, that will always give you something non-zero because, well, Z is non-zero if it defines an element of complex projective space. Okay, so we have this embedding of CPN into some larger complex manifold. And now we can essentially just look at the restriction of all these holomorphic functions on CPN, on this extended CPN back to CPN. So we take a holomorphic function on this extended CPN, and then it turns out that it is already uniquely determined by its restriction to the regular one. So you might know this from complex analysis and several complex variables. If you have a holomorphic function, then it's already uniquely determined by its restriction to the anti-diagonal. Okay, so in particular, what this tells us is that this sort of restriction map is injective. Or in other words, if you just define A of CPN as the image of this restriction map, then we again obtain an algebra, and it is actually going to be isomorphic to the holomorphic functions on this extended space. Okay, and now the last thing that I need to tell you is that, well, the polynomials on CPN, they are first of all really a subset of these analytic functions. And secondly, if you take the holomorphic functions on CPN, on this extended CPN, then there is a topology, which is just a topology of local uniform convergence. And the holomorphic functions are complete with respect to that topology. So we can just consider the corresponding topology on these analytic functions by using this isomorphism. And then the polynomials will be dense. Okay, what is the idea now? Let me maybe just go back. I already said the role of P will be, these polynomials on CPN, they will play the role of P. And well, these analytic functions, they will essentially be the completion. And here is now a theorem essentially about SU1 plus n equivariant quantization of complex projective space. And well, remember that in the case n equals 1, we just have SU2 equivariant quantization of the 2 sphere, and SU2 could also be replaced by SO3 in this context. So that solves sort of the problem from the beginning. And well, what this theorem says for basically every value of h bar that is not an inverse of a natural number, there is some SU1 plus n equivariant product on this algebra that I just described to you. Okay, and okay, so there is this, I should say, I formulated this as an existence result. That is mainly because I don't have time to explain to you how this product is actually constructed in this first half of the talk. I will do that in the second half, but this is really not an existence result. This is really very explicit. So we really start by constructing a formal star product and then basically using this approach that I outlined to you in the beginning, that it is well defined on polynomials and extends to this algebra. Okay, finally, I should also tell you what a Frechet algebra is. Essentially, a Frechet algebra is just a Frechet space, meaning it's some locally convex vector space with the topology defined by countably many semi-norms, and that is complete. And so if you remember how we defined the topology on there, we just took the topology of local uniform convergence on the space of holomorphic functions, and that is indeed induced by countably many semi-norms, and indeed that space is complete. So we really have a Frechet space, and now Frechet algebra just means that this product is continuous with respect to the topology that we just defined. Okay, and here are just two further properties. So first of all, if we take any polynomials, then we really get the correct limit that I wanted to have in the beginning. So if we just look at the product of two polynomials, take the limit h bar tending to 0, then we just get a regular product. And if you look at the commutator, we get I times the Poisson bracket. And furthermore, if you want to study the dependence of this product on h bar, then it turns out that that is very nice because it's going to be holomorphic. Okay. So far, so good. I mentioned that essentially the very same thing works for coadjoint orbits. So let me just state the theorem here, which is essentially exactly the same as this theorem, except for that we need to allow for a countable set of poles accumulating only at 0, and then everything works for h bar not in this set of poles. And I did
Philipp,
yes.
It's a 5-minute warning.
Yes, sure. And what was I about to say? That this algebra of analytic functions on the coadjoint orbit can be essentially defined exactly the same way as before for CPN, where the idea is that this CPN hat, so this extended CPN is just the complexification of this orbit, and then everything goes through just as before. Okay, and here's basically a summary of what I just did. So the idea is of this whole construction is really work with the complexifications, or really work with these extended phase spaces instead of the usual CPN or the usual coadjoint orbit, because then, well, there is a construction of Alexeev and Lachowska of such a star product on the holomorphic functions. That will be the input to all what I said, and then we can basically run this procedure that I outlined here by just restricting everything to polynomials or holomorphic polynomials on this extension, then doing the completion, for which it is actually important that we work with holomorphic functions, because we need a lot of tools from complex analysis, and then restrict ourselves to the real forms in the very end. And there's one direct consequence of that approach, namely if we now take two different real orbits which have the same complexification, because we really just quantize the complexifications and then restrict to the orbit, and then the restriction in the end is actually an isomorphism on this algebra of analytic functions. We get isomorphic Frechet algebras if we start with real orbits that have the same complexification. But there is one thing, if we also consider star involutions on these algebras, then this isomorphism will not be compatible with the star involutions. I should just point that out. Okay, and finally, to round this off, let me just tell you why you might want to care about these Frechet algebras. And the idea there is that essentially the construction that I presented to you did not consider the poles, but there is something that you can do at the poles. And if you do that, essentially, said differently, if you describe the star product by explicit formulas, then you will notice that these formulas stay well defined at the poles, or at these values 1 over n, but only on polynomials up to a certain degree. So only on polynomials up to a certain degree n. And if you know a bit about geometric quantization or Berezin-Toeplitz quantization, then you actually get exactly some finite dimensional algebras at these discrete values of h bar that approximate for you the smooth functions on CPN. And well, in this approach, these algebras coincide exactly with the Berezin quantization. So in a sense, what this result tells us is that the Frechet algebras that I just described, they somehow smoothly interpolate between these finite dimensional algebras that you obtain with Berezin quantization, and well, that could be very interesting to study. Or said differently, if you view it representation theoretic, then you somehow get some infinite dimensional representations or something that's smoothly interpolated between the finite dimensional representations that are relevant for defining this Bayesian quantization. And well, with that, I would like to thank you for your attention and say that in my second part of the talk, I will essentially try to go through these steps again and just tell you in more detail what coadjoint orbits are, what complexifications of coadjoint orbits are, how the star product is constructed, and so on and so forth. Thanks.
Thank you very much, Philipp. Thank you for a really wonderful talk.